Hi. In the previous lectures we've talked about how when solving problems people have perspectives, representations of the problem, and then they have heuristics, which are techniques they use to find solutions given the representation. But we've been focusing on individual problems, individual solutions. In this lecture, what I want to do is I want to talk about recombination. So once I've got a solution, or even once I've got a heuristic, how I can recombine those to come up with even more solutions or more heuristics. And we're going to see the awesome power of recombination. Now remember, stepping way back for a second, we've been trying to think about innovation in the previous lecture. Where does innovation come from? What we're going to see is that recombination is incredibly powerful. And if we have a few solutions or a few heuristics, we can combine those to create ever more. And that may be the real driving force behind innovation in the economy, is that when we come up with a solution, we can then recombine it with all sorts of other solutions, and that leads to ever more innovation. Let me give an example to sort of show how this works. Think about those, math tests or IQ tests you might take online. And they might give you a question like this: 1, 2, 3, 5, blank, 13. You've got to ask what number goes in there, right? And the answer here is just 8. You can get this either one of two ways. You can do 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 8 is 13, and so on. Or you can subtract. 13 minus 8 is 5, 8 minus 5 is 3, and so on. Here's another one: 1, 4, blank, 15, or 16, 25, 36, right? The answer here is 9, and this is just squares. They can also come up with very hard ones: 1, 2, 6, blank, 1806. Now I don't put this on here to make us not feel intelligent. I just want to show you that these can be hard. And I want to show the power of recombination. The first one, which was very easy, required subtraction. The second one, which was harder, involved squares. This one, which seems almost impossible, just requires combining those two techniques. Let's think about it. What's 2 minus 1? That's 1, but that's also 1 squared. What's 6 minus 2? That's 4, but that's also 2 squared. What's 42 minus 6? That's 36, which is 6 squared. And what's 1806 minus 42? That's 1764, which is 42 squared. So the answer to this one, 42, could be gotten by realizing just combine the first two tricks, squaring and subtracting, and that gives us the answer. Well, this idea that you can recombine is really a driver of economic growth generally, and also a driver of science, because when you come up with a new solution, we can combine that solution with other solutions, and we get this geometric explosion in the number of possibilities. To show you how that geometric explosion works, I want to just do a little bit of math. So let's start with something simple, then we'll do something more complicated. Suppose I've got 10 possible solutions or techniques I can use, and I want to just pick 3 of them. I can think of this as the following mathematical problem. I've got a box with 10 objects, and I just want to pick 3 objects from those 10. How many ways to do it? Well, there's 10 things I could pick first, 9 things I could pick second, and 8 things I could pick third. This actually, though, overstates the total number, because if I pick object A and then object B and then object C, that's the same thing as picking C and then B and then A, or C and then A and then B. So if I think about those 3 objects, there's 3 things I could pick first, 2 things I could have picked second, and 1 thing I could pick third. So these are the different ways of arranging those 3 objects. So I get 10 times 9 times 8 divided by 3 times 2 times 1, which is 120. So if I have 10 solutions, or 10 technologies, or 10 heuristics, or 10 ideas, that gives me 120 combinations of 3. Now 120 doesn't seem very big, and it's not, but the point is we've got way more than 10 solutions, and way more than 10 heuristics, and way more than 10 scientific theories. We've got a ton of them. So let's blow up the numbers a little bit. Let's suppose you have a deck of cards. Suppose I have 52 cards in a deck, and I want to just combine 20 of them. How big of a number do I get then? Well, there's 52 cards I could pick first, 51 second, and so on, all the way down to 33 cards I could pick for the 20th. But now that I've got those 20 cards, I could have picked those same 20 cards in lots of different orders. So any one of 20 could have been picked first, any one of 19 could have been picked second, and so on. So my answer is going to be 52 times 51 times 50, all the way down to times 33, divided by 20 times 19 times 18 times so on. That's going to be the number of ways to pick 20 cards from 52. Well, how big is that? Huge. It's 125 trillion. So when you think about combining technologies, combining heuristics, combining ideas, we get this huge explosion. And every time anybody has an idea, it can combine with every other idea and every other combination of ideas. And this may be a big reason why we see so much growth, why we've been able to sustain growth. So think back to our economic growth model, right? Remember we had that like A times capital to the beta times labor to the 1 minus beta thing, and A was the technology parameter. Well, and for sustained growth, we needed that A to get bigger and bigger and bigger. Well, one thing that makes that A bigger and bigger and bigger is when people have ideas, they can be recombined with every other idea, which leads to more and more growth. This idea of ideas building on ideas is the foundation of a theory of economic growth due to Martin Weitzman, who's at Harvard, called recombinant growth. And the idea is ideas get generated all the time. You know, the steam engine gets developed, the gasoline engine gets developed, the microprocessor gets developed, and all these things get recombined into interesting combinations. And those combinations, in turn, get recombined, right, to create ever more growth. So that's the basic idea behind recombinant growth. So if you take something like the steam engine, right, here's a picture of the early Newcomen atmospheric engine, which is really just a steam engine, right? It's got all these things. It's got pumps, right? It's got a steam piston. It's got a boiler, right? It's got a water reservoir. It's got this little like level thing like a teeter-totter. These are all solutions to previous problems. If you think of the gasoline engine, right, it's also got pistons and fuel injectors and all that sort of stuff. It consists of recombinations of all sorts of different problems. So what we get, right, is these big machines, or even the computer on your desk, right? It consists of solutions to all sorts of other problems. So a lot of our inventions are recombinations of old solutions. Take a car. Your car consists of an engine, wheels, steering mechanisms, now consists of all sorts of electronic stuff. So a car, even though it's a solution to a problem, is comprised of a whole bunch of solutions to other problems combined in interesting ways. So it's this recombinations that can drive a lot of growth. When you think about all those parts that went into the car and the steam engine, they weren't developed with the car and the steam engine in mind. They were developed for other purposes. And this is an idea from biology called acceptation. Now, the classic example of acceptation is the feather. Birds developed feathers primarily to keep themselves warm, but eventually those same feathers allowed them to fly. So acceptation simply means this. You come up with some innovation, some solution for one reason, but then it gets exapted, it gets used in another context. So Emily Dickinson famously said, hope is the thing with feathers. It's a good thing to keep in mind, right? Because feathers are this classic example of acceptation. And hope, innovation, change is the thing with feathers as well, right? It's our ability to take a solution for one problem and apply it to something new. What do I mean? Take the laser. The laser was not developed. When they came up with the laser, they didn't think, wow, we can now have laser printers. We can have laser pointers. No, that wasn't what they were thinking at all. They just came up with the laser. So once something's developed, it gets used for all sorts of things that were never expected through this power of recombination. Even perspectives do. So remember my sort of silly perspective on the candy bar, the masticity perspective? Well, you might think, you know, that doesn't really make a lot of sense. Masticity doesn't make a lot of sense as a perspective. It's a sort of a useless perspective. But in fact, masticity might be a really useful perspective for other problems. For example, if I'm coming up with pasta or breakfast cereal or something like that, there may be that sort of a sweet spot in terms of masticity. So that could be a really good way of looking at those problems. So even failed solutions for one problem may work really well as solutions to other problems. So the famous example here, right, is the Post-it note. That the glue that's used in Post-it notes was originally sort of a failure. It was a glue that didn't stick very well. But it turned out to be useful for other sorts of problems, namely making sticky notes. Now there's more to it than this, though. So it's not just the recombination of ideas, because for hundreds, thousands of years, people had ideas. And here's where we've got to sort of reach just one level deeper. If you think about why we've had such sustained growth, how is it that these ideas have been able to be recombined? We have to recognize there had to be some way to communicate those ideas. So Joe Mulcure wrote a wonderful book called The Gifts of Athena. In The Gifts of Athena, he talks about how the rise of things like modern universities, printing press, and scientific communication allowed ideas to be transferred from one location and one person to another. And so it really led to this, huge burst of activity, sometimes called the technological revolution, was the fact that we can now share those ideas and then recombine them. Because, like a tree, if an idea falls in a forest, nobody hears it, and nothing happens to it. So where are we? Here's where we are. We think about innovation. We think about problem solving. Several things going on. First is you have to represent that problem in some way. Second thing is you got to have some way of looking for solutions to that problem. Different people represent problems in different ways. Different people look for different solutions to problems. That means different people can help one another out through that diversity. Second thing, once somebody finds a solution to a problem, or once somebody comes up with some sort of product, or even comes up with a representation, like a perspective, or a heuristic, that can be recombined with all the other ways of thinking and all the other solutions we have to lead to ever more growth. So if you want to ask where does innovation come from, it comes from two things. It comes from diversity of perspectives and heuristics, and it comes from recombination of those new ideas. And that's what allows for ever improving solutions to problems and ever improving new ideas, new products, new technologies, and new policies. Thank you.